Hello. Okay, so let's review what we said last time about conditional probabilities. So suppose that we have a probability triple. So we have a sample space omega, a sigma algebra defined on that sample space, and then a probability measure that takes each element in the sigma algebra and associates it with 0 up to 1. Then let's choose an event. So basically this is a subset of big omega that is included in the sigma algebra, and suppose that the probability assigned to this event B is strictly positive. So we define the conditional probability measure given B as, if we want to compute this probability of some A, that is another event, another subset of big omega included in the sigma algebra, then basically this is how it's defined. So we compute the probability of A intersection B, and this is guaranteed to be in the sigma algebra with a well-defined probability, because if A and B are in the sigma algebra, then the intersection is in the sigma algebra. And then we divide by the probability of B, and that's the reason we insist that the probability of B is strictly positive. Okay, so this operation here will result in what we proved last time to be a new probability measure. Okay, so you start with some probability measure, then you pick an event that is basically assigned a strictly positive probability under that probability measure, and then you can derive basically new so-called conditional probability measures by basically doing this operation here. Okay, so let's take an example. So let's take omega to be ABC. Let's take the sigma algebra. This is a finite set. We said that for finite and countably infinite sets, you can just go for the power set as your sigma algebra, and you choose all possible subsets of big omega in your collection. So we'll choose the power set as our sigma algebra, and then we will do these probability assignments. Of course, we are under obligation to assign basically a probability of 0 to the empty set, a probability of 1 to big omega, and then for A, we will assign it a probability P, which is a strictly, basically, it's in the open interval from 0 to 1, so it's not 0, it's not 1. And then we will basically assign probability Q to this singleton set here. And then we know that A union B union C will give us omega. So these three guys together, their union will give us the sample space, and so the sum of their probabilities should be equal to 1. And so if this is B, if this is Q, then this guy should be 1 minus B minus Q. We don't have any choice. And of course, if I write down something like this, 1 minus B minus Q, I am assuming that basically P plus Q is something that is not above 1, because if it's above 1, then this guy will be negative, and we don't have negative probabilities. So here, that's the third assumption, that P plus Q is less than 1. We'll take it also to be strictly less than 1. Okay, and then what is the probability of A comma B? Then basically this is the union. This is A union B, and so the probability of the sum. So this is P plus Q. A comma C will be this guy here plus this guy. So P plus 1 minus P minus Q. So P with cancels minus P, and we are left with 1 minus Q. P and C will give us 1 minus P, and so this is the probability measure that is basically imposed on measure space composed of big omega and its sigma algebra, which is its power set. Now we can pick up, so of course we cannot condition on the empty set, right? We cannot condition on the empty set, because the empty set by definition, it has a probability of 0, and we do not condition on events with 0 probability. So we will not condition on omega, but on the empty set phi, but we can condition, for example, on this event. So we can construct a new probability measure, which is basically we condition on A. And sort of the practical meaning of this, when you condition on some event, it's like you are sure, this event has already occurred. Okay, so this event has already happened. It's given. Okay, it is given. So that's the reason sometimes we say given A, given. So rather than say conditioned on A, sometimes we say given A. So it's as if it happened. Okay, it occurred. Okay. So if we follow the rule, which is that if you want basically to assign probabilities to all the guys in the sigma algebra, what you need to do is to find is to compose a ratio. And this ratio in the numerator, we have the probability of the intersection of the event with the event we are conditioning on. And in the denominator, we have the probability of the event we are conditioning on. Okay, so what is this probability? So what is the probability of A given A? It's basically the probability of, and you do the intersection, and the intersection of a set with itself is the set. And so this is the probability of A divided by the probability of A, and so this will give us 1. Right? So so you ask, so we know that A has occurred, and so we ask ourselves, what is the probability that A, what is the probability of A, that A happens? Well, A happened already, so this probability here is 1. So the definition actually sort of is consistent with our intuition. What about B? What is the probability of B given A? Then in that case, again, you just apply the formula, and the formula tells you that you compute the probability of the intersection. And now these two guys, each one of them, so these are singleton subsets of big omega, and each element, like A and B, they are distinct elements in big omega. The intersection is empty. Okay, so A intersect B is empty, and the probability of the empty set is 0, and so 0 over a positive number is 0. Right, and this also makes sense because it's like A happened. So what is the probability of B? Well, A happened. That's it. Okay, so this will be 0. Same story for C. So the probability of C given A is 0. What is the probability of A, comma B? So again, this is sort of, you can say that this is A union B, or you can use the word or, right? So you can use union or, and so this is the probability of A or B. So given that A happened, then yes, then A or B is true. Okay, so again, if you check the definition, you will take this set here. You take its intersection with the set we are conditioning on, which is the singleton subset of omega containing the element small a, and the intersection is just this, and the probability will be again some positive number divided by itself. So this will give you 1. A and C also 1 because A is there, but B and C. So what's the probability that B or C, given that A has occurred? Well, if A has occurred, then that's it. Then no B, no C. And again, if you check the formula, the intersection is the empty set phi. So the probability of phi is 0. 0 over a positive number is 0. And of course, the probability of A, comma B, comma C, A or B or C, then A, and A happened, then that's it, that the probability is 1, and again, the formula will give you the same result. Okay, so here you see that our new probability measure, the conditional probability measure, basically choosing the singleton subset of omega, basically containing the element A, then this is just zeros and 1. It's a perfect probability measure, no problems. And in the previous lecture we proved that basically you are guaranteed, if you play this game, you are guaranteed to get something that is valid as a probability measure. Now what if we condition on basically A, comma B? So here again the intuitive thing will be A happened or B, A or B. Okay, so A union B or A or B. So now, okay, the empty set again, its intersection with any set is empty, so the probability will be 0 over something positive, so that's 0. Okay, so, this is what we have. But now, what is this probability? So now this is more interesting than in the previous result. So what is this? What is, A, I can say it like this, probability of A given A or B. Probability of A given A or B. Then so it's like that A or B, one of them has occurred. So what is the probability that actually what has occurred is A, not B, it's A. Okay, so let's apply the formula. So for the formula, again, you will do the probability of the intersection divided by the probability of the event you are conditioning on. Now we are conditioning on the event AB, A comma B, and so this is B plus Q. Now in the numerator, we have the probability of the event A intersection A comma B, and so the intersection is A, and probability of A is P. And so basically this conditional probability here is P divided P plus Q. And if you ask yourself about the probability of B given A or B, then it is Q over P plus Q, right? So again, what happened here is the following, and actually, let me say this before proceeding. The probability of C given A comma B, basically the intersection of C and those guys is 0, and so this is 0. So now, if you have only 3 possibilities, so this is our sample space, right? Our sample space basically it consists of all all elementary outcomes that can that we can obtain in a random experiment. So we can get A, we can get B, we can get C, right? So if we know that it's A or B, then what is your basically what is the likelihood of obtaining C? Well, it's A or B, So conditioning on it's like this has occurred already. So A or B. So it's true that it's A or B, then C is now excluded, and so now when you condition on AB, then the probability of the C becomes 0. What probability of A and B? You will find that basically the probability of A is P, which is its original probability under the original probability measure. But now, given that C is excluded because we are conditioning on A or B, then you just scale this B, you divide it by P plus Q, which is the sum of the probability of P and the probability of A, right? So now the probability of A given A comma B will be P divided by P plus Q, and for the probability of P it will be Q over P plus Q. It's as if we are basically constraining our sample space. So when we condition on A comma B, like this is like sort of the intuitive understanding is that like now we are excluding C. We're saying for some reason we know C is it will not be there. Okay, so when you condition on A or B, it's like you are restricting our set of possible outcomes to A and B. Okay, and so the probability of A will be P over P plus Q, and the probability of P will be Q over P plus Q. And you note, of course, that the sum of these two guys is equal to 1. Okay, again, because it's like now it's A or B, because like C is out of this. We don't expect it. Given that we do this condition. So this is the way of like thinking about conditional probability. And of course, it's in probability theory, it's basically the formula. Okay, so the formula and our intuitive understanding of these formulas is basically very, very nice and very useful in practice in the vast majority of cases. We will talk shortly about like cases in which like things the formulas do not give like results that are like so intuitive. But in the vast majority of cases, actually, the intuitive understanding is very fine. Okay, so let's go back. And again, as I said last time, once you prove that conditioning on an event, and of course, this event should have a strictly positive probability, is actually a new probability measure. If it's a new probability measure, then you expect every property of a probability measure to apply. So basically the probability of A given B, or A conditioned on B, plus the probability of A complement given B, the sum of these two guys should give you 1. Now, if A is contained in C, then the probability of A given B is less than or equal to the probability of C given B. Okay. Now you have the inclusion and exclusion principle. So basically, probability of union is first guy, second guy, then minus the intersection. But what you do right now is that everything is now conditioned on B. This will be valid again because conditioning on B does not give you a new animal. What you have is still a valid probability measure. Okay, so now in practice, like when you are computing probability, sometimes it's very difficult to handle the probability of an event like directly, and so sometimes it's very useful to use the trick called the law of total probability. And so here it is. So the probability of A, what is the probability of A? The probability of A is, you can always write A as A intersection big omega, because A is a subset of big omega, so their intersection is A itself. And then you can partition big omega, okay? So you can partition big omega, which means that you can basically express big omega as a union of disjoint, basically, subsets of big omega. Here again we can write omega. We can write omega as a union of a bunch of subsets of big omega. So those guys, they are disjoint, so their intersection is empty. Pi intersection bj is empty so long as I is not equal to j. But the union basically gives you the full sample space. Okay, so the b's are a partition of big omega. Okay, so again, you take A, you write A as A intersection omega, okay, and then you write omega itself as the union, the finite, in some cases it's finite, in some other cases it's the countably infinite union of, again, of subsets of big omega that are disjoint. Now, A intersection, a union of guys, it's basically equivalent, it's equal to the intersection of the unions. And now, B's are disjoint, and each one of those guys is a subset of bi, so those guys themselves are disjoint. And now we can apply the axiom of a probability measure that there is nothing called a probability measure unless it is countably additive, which means that the probability of a union of disjoint events is the sum of probabilities. So because those guys are disjoint, then the probability of the union is the sum of their probabilities. Okay. And so this is the first form, okay, that we have here. It's general and very useful. And its usefulness is because sometimes those events are much easier to basically when you compute basically the probabilities. Okay, so sometimes this A itself is complicated, but A intersection pi for every I is like sort of straightforward, and so you can compute the probability of those events and then sum them, and then you will get the probability of A. Okay, again, this is not true unless those PIs partition omega. So what you use here for PI are something, again, the intersection is empty, but for any I not equal to j, and their union should basically exhaust big omega. Okay, so this is the first form of the law of total probability, and we can take it a step further. If basically the PIs they have non-zero probability, so basically the probability of PI is strictly positive, then, so remember that we have what is the probability of A given PI. So if the probability of PI is not zero, this is well defined. We can define this thing, and what it is basically is the probability of the intersection divided by the probability of PI, right? So what you can do is that you can simply say that the probability of the intersection is this product. Okay, so the other form is that the probability of A is summation I from 1 to infinity, the probability of A given BI multiplied by the probability PI. Okay, so this is the law of total probability. If in case you can write it, you can write the probability of the intersection as the product of this conditional probability and the probability of each PI. The subtlety here again is that you cannot condition all events that have a probability that is equal to 0. So like going from here to there, you are sort of assuming that basically you can condition. It is well defined to condition on PI. Okay, so those guys are the law of total probability. Very useful, and we will later in the lecture solve an example. Using the law of total probability. Okay. Now, again, inspired by what I did here. So you can, so suppose that you are talking about two events. Okay, so let's take that probability of A is greater than 0, right? So if the probability of A is greater than 0, then you can condition on A. And so you can take PIs and you can find the probability of PI given A. Now again, we are able to condition on A because the probability of A is strictly positive. By definition, this will be the probability of the intersection divided by the probability of A. Okay, now suppose also that the PIs, like here, that the PIs, each of them is basically strictly positive. So this is strictly positive for every I. then you can write this intersection in the other way that I used previously, that you can write the probability of PI intersection A is the probability of A intersection PI multiplied by the probability of PI. Okay, so this will be the numerator. Okay, and to the denominator we can apply this. We can apply this formula here. You know, the law of total probability, and write that probability of A is the summation G from 1 to infinity, probability of A given Pj, probability of Pj. Okay, so this is called the base rule, and it is very fundamental, very useful also. Okay, you know, if we can write a simplified version. So suppose that A and let's say C, the probability are events, and probability of A, so both of them are in the same. Probability of A is greater than 0. Probability of C is also greater than 0. Right? So now, because both events have a strictly positive probability, we can define conditional probability given, you know, conditioned on A or conditioned on C. So this is something that makes sense. Okay, and also this is something that makes sense. And the first one is the probability of the intersection divided by the probability of the event that we are conditioning on. The second guy is the same. So A intersection C divided by the probability of A, right? So if you compare, now you can write basically the probability of A intersection C. Okay, so from here you can say that the probability of A intersection C, you can write it as the probability of A given C, probability of C. So from this here, or you know, you can write the probability of the intersection as the probability of A or C given A, okay, multiplied by the probability of A. Okay. So this is again, if it's meaningful to define conditional probabilities, you know, because our events have strictly positive probabilities, then we can take the probability of the intersection of two events and we can write it in this way. Again, why? Because it's useful, you know, as we'll see in the examples. So the probability of A intersection C, it is probability of A given C multiplied by the probability of C, or you know, maybe it's A. I mean, sometimes one of those guys is difficult and the other is easy. So I mean, which form to use? We use this form or that form. Sometimes probability of A given C is like sort of very straightforward. The other one is like is difficult, or vice versa. Okay, so but you know, you can do this or that, and of course, like you will, you know, when you're trying to solve a problem, you will experiment, and if something seems like intractable, you just, you know, switch to another basically strategy or another trick. So probability of A given C multiplied by the probability of C, or probability of given A multiplied by the probability of A. These two guys are the same, and they are equal to the probability of the intersection. Now, if we have something more complicated, like here, you know, if we have a bunch of events, again, like in the previous point, which basically partition omega, and they are pairwise disjoint, then we can write the probability of Pi given A as the probability of the intersection divided by the probability of A. Then the probability of intersection can be written as the probability of A given Pi, probability of Pi, and the probability of A itself can be expanded using the law of total probability. And so it is given by the sum here, which is equal to summation G from 1 to infinity, the probability of A intersection Bj. Okay. So also we can have like the product rule. The product rule is also very useful, and this is its general form. It's basically a generalization of this idea here. So what is the probability of the intersection? So we see now that we can write the probability of the intersection, you know, if the conditional probabilities are well defined. So this is probability of A1, right, multiplied by the probability of A2 given A1, right? So again, this is by the definition of the conditional probability. So the conditional probability itself, you just move this downstairs. Probability of A2 given A1 is the probability of the intersection divided by the probability of A1, so long as it is not 0. So the probability of the intersection is the probability of A1 multiplied by the probability of A2 given A1. What if you have 3 events? Okay, so 3 events, A1, intersection A2, intersection A3. So, well, this is the probability. This is the probability of. So you can think of these two guys together. Okay, so this is the probability of A1, like here, and then the probability of A2 intersection A3 given A1. Okay, and then you can repeat the trick again. You say this is probability A1. Now we have the probability of an intersection given A1. Like in the first case, we can basically apply the trick here, but now conditioned on A1. So this is the probability of A2, right? If we don't have condition, so let me put it here, the probability of A2 intersection A3. What is this thing? You can write it as probability A2 multiplied by the probability of A3 given A2. Right? Again, from the definition of conditional probability. Now, since you are conditioning on A1, then this thing here, you can show that it is probability of A2. Now you condition on A1, so it's A2 given A1, probability of A3 given A2 and A1. Okay, and then you can see that there is a pattern here. So the probability of an intersection, so it's the probability of the first guy, then multiplied by the probability of the second guy conditioned on the first guy, times the probability of the third guy conditioned on basically the intersection of the two first guys, and so on and so forth. In fact, this is true for any finite n, and it is true also if basically you have an uncountably infinite collection of events. And you will see the proof of this in the coming tutorial session. Okay, so something like this, you can just it's easy when the number of random variables is 2 is sort of by definition. From the definition of conditional probability, you have this this way of writing the probability of the intersection. Then you can just do induction, right? So you can do induction and simply prove things for a general n, and then you can if you have basically an infinity of those events, then we know the trick now. So it's the continuity of probability. Continuity of probability always allows you to basically take a finite union or intersection and basically compute the probability of an infinite union or intersection. Of course, by infinite, it should be countably infinite. Okay? Before doing solving some examples, I mean, let's also finish the concept of independence. And the two events are said to be independent under a probability measure. So it's always your starting case is always the triple, the sample space, the sigma algebra defined on the sample space, and the probability measure. Two events are independent if you can if it is true that the probability of the intersection is the product of the respective probabilities. So this is sort of the mathematical and the dry definition of independence. Again, it is two events are independent if the probability of their intersection is exactly equal to the product of probabilities. Okay, and this is the main definition. So the main definition of independence is not something related to conditional probability. Okay, it may be related to conditional probability, but this is the main definition. Now, if it happens that the probability of B is strictly positive, then you can define the probability of A given B. So the probability of A given B, again by definition, is the probability of the intersection divided by the probability of B. Now, if A and B are independent, then according to the definition of independence, you can take the probability of their intersection and express this probability as the product of two probabilities, P of A times P of B. Now, this guy will go with this guy, so you have a common positive number in the numerator and denominator, so you can just eliminate this number, and you are left with the probability of A. So, if A and B are independent, so if these two guys are independent, and moreover, the probability of B is greater than 0, which means that B is an event we can condition on, then in that case, the probability of A given B is equal to the probability of A. Okay, so here's the sort of the intuitive understanding that what does it mean that you condition on B you compute the conditional probability of A given B, and you get the probability of A. So you get the original probability of A. Conditioning on B does not change the probability assigned to A. You assign, so again, you start with a triple, the sample space, the sigma algebra, and B. Then you assign a probability to A. Now you say, okay, let's play the game of conditioning. You choose B, which is an event of strictly positive probability. You condition on B, so you have a new probability measure. But then you compute what is the probability of event A under this new probability measure, which is the probability measure when we condition on B, and you get the exact same probability of A. So we say that A and B are independent, in that case, meaning, again, the intuitive meaning is like B tells us nothing about A. So if B has occurred, given B, basically our knowledge about A is the same. Our knowledge about A is the same. Nothing changes regarding A. The probability of A is the same, given B, conditioned on B, if B has occurred. Okay, so independence here again will tell you, again, this is the intuitive understanding, that A and B are independent. It means that, observing B, if we observe B, we gain no knowledge, no information about A. If we observe B, if B has occurred, given B, conditioned on B, A, probability of A remains the same. So no knowledge is gained about A by observing B. So this is sort of the intuitive meaning of two events being independent of one another. Okay, but the mathematical definition is very strict and very dry. It is simply, you take two events, A and B, you say that they are independent if the probability of the intersection is the product of probabilities. Okay, so let's take big omega. Let's take big omega to be the closed interval from 0 to 1. Now we know from the previous lecture that it is not feasible to get meaningful results, consistent results, if we choose the power set as our sigma algebra. So in our case here, we choose the Poel sigma algebra on 0, 1 as our sigma algebra. And remember, so there is something called the Poel sigma algebra on R. Okay, and so remember from the previous lecture, this is basically a sigma algebra that is generated by by all possible open intervals on the real line. And this sigma algebra, you start with the open intervals, but a sigma algebra basically is closed under complementation and finite and countably infinite unions and intersections. So you start with the open intervals, but you end up containing all the singleton subsets of R, all the closed intervals, and many other subsets, including something like the Cantor set. Okay, so if you take the Poel sigma algebra on R and intersect each of its members with the closed interval 0, 1, you are guaranteed to get a sigma algebra on basically the closed interval 0, 1, and it will be called the Poel sigma field or sigma algebra on the closed interval 0, 1. And let's now have the uniform measure. Okay, let's define two events. So A is basically rational. So like A is actually the set of rational numbers. So A is the rational numbers living in 0, 1. B irrational. So B is, the irrational numbers living between 0 and 1. Okay, so those are A and B. Now, what is the probability of A intersection B? So basically, if you are not rational, you are irrational, right? So this is this is how real numbers are basically classified. So each real number is either rational or irrational. That's it. Okay, there is no third possibility. These two are mutually exclusive, right? If you are rational, you are not irrational, and vice versa. So the intersection is empty, and so the probability of A intersection B is basically the probability of the empty set, because the intersection of A and B is empty, and the probability of the empty set is, for any valid probability measure, this is equal to 0. So the probability of A intersection B is exactly equal to 0. Now, what is the probability of A? So it is 0. Why it's 0? I mean, so this is 0 because A is a countably infinite subset of 0, 1. So remember when we talked about this probability space. So in this probability space, the singleton subsets, which are all in the Poral sigma algebra on 0, 1, the singletons are assigned the probability 0. And if the singletons are assigned the probability 0, then any set, basically that is a finite union or a countably infinite union of the singletons, something like, the rational numbers on 0, 1, this will also be with probability 0, right? Because the probability of the union will be 0 plus 0 plus 0 plus 0 and so on. So it's 0. It's just 0. So the probability of A is 0, which means that, again, the probability of under the uniform measure, if the probability of a rational number, basically Q intersection 0, 1, is exactly equal to 0. Now, what about the probability B? Well, I mean, what about the irrational numbers? Of course, the irrational numbers are uncountably infinite. And the irrational numbers, basically the probability of B is 1 minus the probability of A. I mean, because A and B are basically the complement of one another. And so the probability of B is equal to 1. And so what is the product of these two probabilities? So one of them is equal to 0. One of them is equal to 1. So the product of the probabilities is equal to 0. So A and B are independent. So these two events here are independent. Okay? From the definition of independence. The definition of independence tells you you want to check whether A and B are independent, go and compute the probability of A, the probability of B, the probability of A intersection. If the probability of A intersection B is exactly equal to the product of the probability of A into the probability of B, then that's it. Their two events are independent. So we did this here, exactly. So the probability of the rational numbers, because they are countably infinite, then this probability is equal to 0 under the uniform measure. Now, the probability of B will be 1 minus 0 because basically B is the complement of A on 0, 1. Now, what is the probability of the intersection? The intersection is the empty set, so the probability is 0. And so 1 times 0 is 0. Okay, so they are independent. But now let's think about the intuitive understanding of independence that I just mentioned. And, I know that some of you have already used it. So if you use probability, then again, you typically think of independence that A and B are independent if observing B tells us nothing about A, right? But this intuitive understanding will fail here, right? So given A, so suppose that you close your eyes, you pick a number on the closed interval 0, 1, and you discover that this number is a rational number. Then you know with certainty that it is not irrational, right? Because if it's rational, then automatically it cannot be irrational. Okay, so basically you intuitively these two events are very related. Like you have only two possibilities, rational or irrational. So if one of them happens, you expect you know that the other will not happen, right? So you pick a rational number, then you know that basically it is not irrational. You are sure now that it is not irrational, or vice versa. If you pick an irrational number, then it is not rational. That's it. So basically picking a number and discovering that it is rational tells you that it cannot be irrational, and vice versa. So they seem to be dependent by our intuitive understanding of independence, because like an observation will tell you everything about the other, but they are independent because basically the mathematical definition is okay here. We verified the mathematical definition, so they are independent. So let's take this a step further. Are there events that are independent of themselves? Okay, so this statement here, an event that is independent of itself, is not. I mean, so you observe A and you say that A does not tell you anything about A. right? So I mean, if this is the intuitive understanding of independence, that you observe an event and it tells you nothing about the other event. So what does it mean actually to ask this question, that an event is independent of itself? So if you think about the definition, the mathematical definition, you find that actually this question is very valid, right? So when is an event independent of itself, just mathematically using the definition? So if probability of A intersection A is equal to the probability of A times the probability of A, then A and A are independent. A is independent of itself. Okay, and so what is the probability? What is the probability of A intersection? What is A intersection A? It's A itself. So this is the probability that A is equal to the probability of square. Okay, so for real numbers, I mean, what are the real numbers for which the number is equal to its square? We have two solutions, right? Exactly, 0 and 1. That's it. So yes, events that have a probability 0 or 1 are independent of themselves. So you can see, the failure of the intuitive understanding of independence, right? But this happens for the extreme case. So here is the good news. The good news is that, like, if you are dealing with events, in which, like, the probability is not 0 or 1, so if you avoid those extremes, if you avoid the extremes of events with 0 probability or 1 probability, then you can go for the intuitive understanding, and you can understand A being independent of B to mean that B tells you nothing about A. Observing B will tell you nothing about A. Okay, but just keep in mind that this intuitive understanding, it has limits, right? Because by the end of the day, the definition of independence is a dry mathematical, basically check. You just compute the probability of the intersection, the product of probabilities. If they are exactly equal, then you have independence. And yes, you can. It is very legitimate in probability theory to talk about events that are independent of themselves, and specifically those are events that are that have the probability 0 or 1. And so what are those, guys? We have a name for them, right? We said, I said it last time. So basically, so A is independent of itself, means that the probability of A is 1. So A, B is almost sure. Okay, so remember this. So this term is, when you say almost sure or almost surely, it means that the probability is equal to 1. Or so A is an almost sure event, or A is the complement of an almost sure event, which means that its probability is 0. Okay, so for events with probability 0 or 1, yes, those events are independent of themselves, despite the fact that this may sound awkward, but it is true. And if you avoid again those extremes, if your events are, with probabilities strictly living between 0 and 1, so strict positive numbers less than 1, then go for the intuitive understanding, and it will work. Okay, but understand the limits of quote-unquote the intuitive understanding. Okay, so A is independent of itself if it is an almost sure event or the complement of an almost sure event. Okay, now we can take the concept of independence and we can basically sort of generalize it to what about the independence of a bunch of events, more than 2, I mean. So basically n events. So n events are said to be independent if, okay, so let's see now the condition of independence. Again, it's the definition of independence is just some mathematical expression that you need to verify. So now, for a bunch of events, for n events to be independent, you simply take, basically, you do a selection of those events. So you can take 2 events at a time, 3 events at a time, 4 events at a time, till you take all of them. And for all cases, it must be that the probability of the intersection is the product of probabilities. Okay, so let's go to the simple case. What if you have 3 events? Then what you do is that you take 2 events at a time. and it must be the case that the probability of intersection is the product. So it must be the case the probability A1 intersection A2 is probability of A1, probability of A2, and the probability of A1 intersection A3 must be the probability of A1, probability of A3, and the probability of A2 intersection A3 must be the probability of A2 intersect multiplied by the probability of A3. Are we done? Not yet. Then we need also to take them 3 at a time. So the probability of A1 intersection A2 intersection A3 should be the probability of A1, probability of A2, probability of A3. Now, to say that A2, A1, A2, A3 are independent, you need these 4 guys to be true. If 3 of those guys are true while the 4th one is not true, then A1, A2, and A3 are not independent. So for independence, it must be the case that these 4, what you can call mathematical statements, should be true. Okay, and yes, you can come up with examples in which like 3 of them are true and 1 is false, and in that case, we do not say that the events are independent. They will be dependent. Okay, so this is just for three events. If you have any events, again, what you do is that you take the events 2 by 2. So you take them in 2s, in 3s, in 4s, in 5s. So what you are doing is that how many of those conditions must be satisfied? So what are the subsets of the set 1, 2, 3 up to n? Now it's 2 to the power n, right? If you exclude the empty subset, this is -1. If you exclude taking the singleton subsets, you take an event on its own, then there are n singleton subsets, so you subtract them. And so these are the number of checks that you need to do if you want to check the independence of n basically events. Okay, so if n is equal to 3, this is 2 to the power 3, which is 8, minus 1, that's 7, minus 3, that's 4. And those are the 4 statements that we need to check if you want to study the independence of 3 events. Now, if n is 4, this will be 2 to the 4, that's 16, minus 1, that's 15, 15 minus 4, 11. So there are 11, basically equalities that you need to check to declare that basically those 4 events are independent. Again, this 2 to the n minus 1 minus n, it's because you take all the events starting, you take them in 2s, and then in 3s, then in 4s, then you take all of them. So it's as if we are basically selecting from a set. So this is the number of subsets of a set, excluding the empty subset and excluding the singleton subsets. Okay, so this is again the number of equalities that we need to check if we want to investigate the independence of any events. Now, what if you have an arbitrary collection of events? So this arbitrary collection of events can be countably infinite, or it can be uncountably infinite. Okay, so in that case, you will need to do the check, that the product of an intersection is equal to the product of probabilities. You need to do it for all possible finite selections of your events. Okay, so you need to take the events in 2s, in 3s, in 4s, in 5s, in 6s, in 7s, and so on, right? So, you basically have to do like an infinity number of checks to make sure that the events are independent. If we are talking about an arbitrary collection of events, and here, of course, I am basically more interested in the infinite case of countably infinite or even uncountably infinite collection of events. There are actually other concepts that are, if we want like to be very rigorous in the understanding of random variables, we should also understand the concepts like the independence of sigma algebras. Okay, so there is this concept, not just the independence of events, but the independence of sigma algebras. But I will skip it here in this course, and I will leave it to a more advanced course on probability theory. Okay, so most likely here we will talk about the independence of events, and when we talk about random variables, we will deal with independence in sort of a pragmatic way, not through sigma algebra. Okay, so that's the story of independence. Again, before going to the next slide, again, for independence, you can stick to the intuitive understanding that that A and B are independent. If observing B does not tell you anything about A, if basically the occurrence of B basically it gives you no knowledge whatsoever about A, this is valid so long as you are avoiding those almost sure and complements of almost sure events. Once one event has a probability 0 or 1, the intuitive understanding of independence may collapse. Okay, so by the end of the day, it is actually a mathematical definition, and the intuition works, and it works actually in many cases in practice. Okay, so here is our first example. So we have a container with n balls. So each ball has a number 1, 2, 3, 4 up to n. Then you choose one randomly, okay, and then you make a decision. Okay, so you take a ball and then you basically observe the number on the ball. So if this number is 1, then you return the ball. Okay, so you back. If it's any other number, you just throw it away, and then you draw a second ball. And so the question is, what is the probability that the second ball carries the number 2? What is the probability that the second ball carries the number 2? Okay. So now here's like why this event is not very straightforward. It's not very straightforward because we are talking now about the ball that is drawn in the second time. So the issue is that we are not very sure regarding the container, right? Because after the first basically draw, if you get a number 1, you will return the ball into the container, and in that case the container has basically the numbers from 1 to n. But if you in the first draw, if the ball has a number other than 1, you will simply discard it. You will throw it away. And now when you do this, your second part of the experiment, now you may have a number missing, right? So you may have 2 missing if 2 was drawn in the first step. You may have 3 missing, and so on and so forth. Okay? So if the event of obtaining 2 in the second draw is like not very straightforward, but it becomes straightforward if we condition on the possibilities that may happen in the first part of the experiment. Okay, so that is basically the law of total probability applied. So the probability so basically let me write the general law of total probability. Probability of A is sum probability of A intersection BI. Okay, and if you can define conditional probabilities, this is the sum probability of A given PI, probability of PI. And don't forget that those PIs, they should do what? They should be disjoint. They should be disjoint, and they should exhaust basically the space of possibilities. Okay, so what we will do here is that we will condition on the number that is in the first draw. This number has exactly n possibilities, and we don't have any other thing. So when you start with basically the balls from 1 to n, and then you choose one of them. So you can obtain 1 or 2 or 3 or 4 up to n. Okay, and so basically you get k in the first row, k from 1 to n. Those are basically your BIs. Those exhaust the space of possibilities because you will just get either 1 or 2 or 3, and of course they are mutually exclusive in the sense that if you get the ball with number, you just draw one ball. So if it carries the number 3, then it does not carry the number 2 or any other number. Okay, so here is the application. So the probability of getting 2 in the second row is the probability of getting 2 in the second row given or conditioned on k in the first row, multiplied by the probability of getting k in the first row. Okay, let's see each one of those guys. What is the probability of getting k in the first row? You draw things only, and basically if nothing is mentioned except that a ball is drawn randomly from the urn and it is returned, then basically each ball has the exact same probability of being selected. Okay, so the probability of k in the first row, this is regardless of k, this is always equal to 1 over n. So this probability will be independent of k, and it is just 1 over n. What's the probability of being 1 over n, 2, 1 over n? Because there are n balls, each one of numbered 1, 2, 3 up to n, and the probability of getting k is basically it's 1 out of n possibilities. So it is 1 over n. Okay, now let's look at the conditional probabilities now. Okay, so what is the probability of getting k? Now the conditioning here makes sense. Conditioning makes sense because you can get 1 in the first row or 2 or 3 or up to n. So basically the events you are conditioning on all have a probability 1 over n, and so that's strictly a positive probability for any finite n. Okay, so this conditional probability now, it will depend on k. It will depend on k, right? So what if k is equal to 1? So what if you basically choose 1? Okay, so now this is the first term here. So this 1 over n that you find there, so this is probability 1 in first row. This is 1 in first row. Now, according to the experiment and how it is designed, now if you see 1, you put it back. You put it back. Okay, so now when you do the second part of the experiment, basically you start with n balls. Each ball has a number. Each ball has basically a number from 1 to n. And so the probability of getting 2 in the second row, given that basically your first number is 1, is 1 over n. Okay, so this is the probability 2 in second row given 1 in first row. In fact, if you get 1 in the first row, in the second row the probability of getting any number is 1 over n. And the reason is basically this step in the experiment, that if you get 1, you put it back. Okay, so that's the first term. So this corresponds like to k equals 1. Now what if k is equal to 2? Now the probability basically that k is equal to 2, so this is the probability of 2 in first row. 1 over n. What will happen now, according to basically the steps of the experiment, now if the first number you get is 2, you don't return it. You simply discard it. You throw it away. So now you are left with balls, numbers 1, 3, 4, 5 up to n. There is no 2. So what is the probability of getting the 2? Now it is equal to 0. Okay, so this is the probability of 2 in second row given 2 in first row, because poor number, if it's selected initially, then the ball carrying this number will be thrown away. It will be excluded from the experiment. So the probability now of getting 2 in the second phase will exactly be 0, because there is actually no ball carrying the number 2. Okay, it was actually thrown away. Now what if k is equal to 3 or k is equal to 4 or 5 or 6 now? Okay, so in all those cases, okay, the probability of So this is probability K in first row, and K can be like 3 or 4 up to N. Now, if you pick any of those numbers, what do? Then you basically throw the ball away. Okay, so if you pick 3, basically, when you do the second phase of the experiment, basically there are n-1 balls. There are n-1, not n. But the ball with the number 2 is there. Okay, it has not been thrown during the, right? And so now the probability, so this is 1 over n, so this is the probability, or 1 over n-1, this is the probability of 2 in second row given K in first row, and K is some number 3 or 4 up to N. Because in this case, it's one of those numbers that will go away, and you are left with n-1 balls, and the probability of getting the ball with number 2 is now 1 over the number of balls, now n-1. And basically, this 1 over n-1 multiplied by 1 over n, it's exactly the same thing you get for 3, 4, 5, 6 up to n. So you can just take this and multiply by n-2. So basically, n-2 are basically the cardinality of this set, 3, 4, up to n. Okay, and then you simplify and you get to this. So this is basically the required probability. And here you see the law of total probability in action, and you see how it simplifies things. Again, having 2 in the second row is not that straightforward, because basically the contents of our urn will depend on what has happened at the first step. So it may contain n balls, it may not contain a ball carrying the number 2, it may contain it and have a total of n-1 balls. So things depend on basically what happened in the first row. So here it makes sense to use the law of total probability and to condition on basically the event, the number that you get in the first row. And now you have those probabilities, you find that they are sort of straightforward to compute, then you compute them and then you sum them to get your final result. Note that here we do not really need to think about big omega or anything, and you are actually advised that if you do not have to think about big omega, don't think about it. Okay, but for completeness, here is the big omega of the experiment, right? So in the experiment you have basically big omega. It's basically a set that has basically order that is composed of ordered pairs, right? Ordered pairs. These ordered pairs give you basically the possible numbers that you get in the first row, comma the possible number that you get in the second row. Okay, and you may basically assign probabilities to each of the. So what is the probability of getting 1 in the first row and 1 in the second row? It is 1 over n squared. Why it's 1 over n squared? In the first row, to get 1, it's 1 over n. Then you return it. So in the second row, you have also n possibilities, and so it is now the probability of getting 1 twice is 1 over n times 1 over n. Okay. So what is the probability that you get 4 in the first row and then let's say 3 in the second row? It is 1 over n-1, and the reason that you get 4, you discard it, and then to get 3 in the second row, now you are choosing a ball out of n-1 balls, and so those are n-1 possibilities, and so the probability will be 1 over n times 1 over n minus 1 over n-1. Okay, and basically this is the sample space with the associated probability. Again, you don't need, if it's not needed, then you just the solution will be just those 3 lines. Okay, now let's do our second example. So we have a disease and a test. Okay, and there is no test that is perfect. No test whatsoever is perfect. And so the test is characterized by the following basically numbers, and let's see them. So if a person has the disease, the test yields a positive result 90% of the time and a negative result 1% of the time. So what does this mean? So basically, someone has a disease. Okay, now you apply the test to the guy. Now the test may tell you, oh yes, the guy has this medical condition, or it may actually fail to detect, basically the disease, whatever, bacteria, virus, whatever. And so what we are saying here is that the probability of saying the guy has the disease, okay, so this is the probability that, the test will give you a positive result. And given that the guy actually has the disease, so again, if we are basically trying to study some disease caused by some virus, and so basically the guy has the virus, so the probability that we say that the guy has the virus will be basically 0.99. Yes, so there are cases, there is a probability 0.01 that the test will fail to detect the presence of the virus. Okay, and so basically the probability of misdetection, okay, given that there is the disease or the virus or whatever, this is 0.0. Okay, so this is the first number that we know about this test. But what if someone does not have the disease? Okay, so someone, again, if we talk about viruses, someone does not have a certain virus, okay, or a certain medical condition or whatever. Then, again, the test will tell you so, but only 95% of the time. So here, this means that the probability, so now we are saying that no disease. So basically the guy is, is okay. The guy is okay. He or she does, they does not have the medical condition that we are trying to test for. But the test, does not necessarily, will not necessarily tell you, oh, this guy is okay, So the probability that the guy, test says no disease, this will happen most of the time, but unfortunately not all of the time. So this is 0.95. And then there is a probability that is 0.05, in which actually we will get a false alarm. Okay, so basically probability of false alarm. False alarm is like when, so there is no disease, okay, there is no virus, for example, and you say, oh, the guy has the virus, okay? So this false alarm, it happens, and it happens with probability 0.05. Okay. Suppose that 0.1% of the population is infected by this disease. So again, we now need to, to have a number regarding, the prevalence of this disease, the spread of this disease in the population. So we know that it's there in 0.1%. So basically in 0.001 of the population is infected by this disease, and the remaining population are basically free from it. Okay. So so this is a long story. So what are we supposed to answer now? So someone, you or me, took the test, and the test is positive. So the test is positive. Okay, so now we are asking this question. See what the probabilities that I keep explaining here are conditioned on whether someone truly has the disease or not. But now we are changing the perspective. Now we know that the test result is positive. So I do the test to someone, and then the test result is positive. So the test is telling, yes, this guy has this disease or this medical condition, this tumor, this type of protein, whatever. What is the probability that the guy actually has the disease? Okay, so being tested positive does not necessarily mean that you have the medical condition or the disease or whatever it is. There is a probability. Okay, so So here is what we are interested in. Okay, so we are interested in the probability of disease given a positive result. So now what we are sure of is that this guy did the test and the test yielded positive result. So the test, according to the test, this guy has the tumor, or these protein markers or whatever. So what is the actual probability that this guy has a disease? Okay. So now the idea is that the numbers that we have up there, all those numbers are the other conditional probabilities, right? So they are basically given the true condition. We are talking about whether the test will yield a positive result or not. Now we are asking it in reverse. We are saying, what is the probability of having the disease given that the result is positive? So the way of going back and forth between these two, like again, conditioned on the actual situation or conditioned on the test, basically, who's our friend here? Bayes rule, right? So what is Bayes rule? Again, Bayes rule, PI given A, remember? So this is the probability of A given PI, probability of PI. Okay, and then we divide by the probability of A, and the probability of A can be written as the sum probability of A intersection PI, and this thing can be written here in terms of the conditional probabilities, probability of A given PI, probability of PI, like this. Okay, so this is our friend here again, because this is the way like to go. So here on the one hand, you basically on the left hand side we have conditioning on A, and here we have conditioning on PIs. So here we have conditioning on the test result being positive. This probability here that you find on the left hand side is typically called the a posteriori probability, or the posterior probability. So it is called posterior. Posterior, it means after the experiment is done. Because now there is a guy who did a test. So the test is done, and we know that the test result is positive. And the question is, given that, what is the probability that the guy actually has the medical condition? Okay, so this is called a posteriori. Posterior means after, so it means after the experiment. Okay, so this is equal to, and we apply Bayes' theorem, okay, or Bayes' law. So the probability of disease given a positive result is probability of positive test given the disease multiplied by the probability of the disease. So these two guys are in the numerator. So like here, PI given A given PI and PI. So here we have positive test given the disease. Okay, so what is this probability? So if someone has the disease, with the probability that the test will be positive, according to the problem statement, this is 99%, which is 0.99. Then here we have the probability of disease. So this is called the prior or a priori probability. So this is the probability without doing any experiment or any test. Okay, so remember that basically this is statement here that in the population, 0.1%, so 1 in 1,000 has the disease or has the medical condition. So if you close your eyes and you pick a person at random from the population, what is the probability that this guy will have the disease? It's without doing any test or anything. So basically it is 0.001. Okay, so this is 0.001, which is the 1%. And it's called the prior or a priori probability because we haven't done a test yet. Okay, so this is this is called the posterior or a posteriori probability. This is called the a priori probability of in our case here, the disease. Okay, I will explain. Those guys, those probabilities here are the likelihoods. Okay, so those are the likelihoods. The other guys, so in blue, this one, so the probability of a positive test given the disease or a positive test given no disease, those are called the likelihoods. Okay, and so near the end of this course, we will study hypothesis testing, and basically we will use this terminology. Prior prior or a priori probabilities, posterior or a posteriori probabilities, and likelihoods. Okay, and so again, this is the posterior probability. Okay, it's the probability of the disease after doing the test. This is the prior probability. It's the probability of the disease without doing the test. It's just based on just making a guess regarding a randomly chosen person from the population. And the other guys here are called the likelihoods. Okay, which are these numbers, 99%, 95%, and so on. Okay, so in the denominator we have the probability of a positive test. Okay, so here the denominator, this is the probability of a positive test. So by the law of total probability, what is the probability of being tested positive? Okay, again, you can say, let's use the law of total probability. We will partition our possibilities into two cases. So disease or no disease, right? So when your test is positive, it may be positive and you have the disease, or it may be positive and you don't have the disease, okay? So we just have two terms here. So the probability of a positive test, it's the probability of the disease multiplied by the probability of being tested positive given the disease, plus the probability of having no disease multiplied by the probability of having a positive test result given no disease. Okay, so here again it's like the law of total probability, but our summation has two terms only, because again we partition our possibilities into just two possibilities: disease or no disease. So a positive test, it may occur and there is the disease is there, or it may be absent. Okay, and so what is the probability of positive test given the disease? Okay, so someone has the disease and he or she is tested positive, that's 99%. The probability of the disease, the prior probability of the disease is 0.001. What is the probability that no disease and someone will have a positive test? Okay, so no. So here, if we go to the second line, so test says no disease, given no disease is 0.95, and the probability of false alarm given basically no disease is 0.05. So this is what we have here, that someone does not have the disease, but unfortunately he or she is tested positive. Okay, and so this is the false alarm. So this is false alarm. Okay, and this probability is 0.05 according to the problem statement. Probability of no disease, this is just 1 minus 0.001, and then you plug in the numbers and you compute and you get 1.94%, which is a small number, by the way, which is a very small number. So so basically if someone is tested positive for a medical case, you may be in a situation in which the actual probability that the guy has the disease is actually very small. So here it's about 2%, 0.02. The probability that the guy has the disease given the positive test is very, very small. The probability that the guy has the disease given a positive test is a complicated thing, as you may see. It depends on the quality of the test. The quality of the test. Okay, and you see that the test has two parameters. Basically the rate of, people call it the rate of false positives and true positives. So, what is the probability of saying that someone has the disease given that he has the disease, or the probability of saying that someone has the disease given that he does not have the disease? Okay, so so basically these parameters will be there, and also the prior probability is very important. Basically, what is the probability, that someone big randomly from the population will have this disease or medical condition or virus or basically DNA sequence or whatever. Okay, so it's a complicated thing, but actually actual life is even more complicated. Actual life is much more complicated, because this problem assumes that we know those numbers. So I will put those numbers in. So this number, that number, and that number in actual life we don't actually know them. We also estimate them, and there is no estimation without an estimation error. Okay, so in actual life, you may think that, this is like sort of, this is like sort of a way to just compute things. No, because for many tests, you may not be able to exactly find this number. Okay, and you'll find you may find disputes regarding. Someone say, oh, the detection probability, the probability that the test will give you a positive result, given that the guy has the disease, is like 99%. So no. We repeated the experiment. We did some experiments, and actually no, it's lower than 90%, and so on. So actually, these numbers are obtained via doing experiments, and when you do experiments and estimate stuff, as we'll talk about later in this course, you don't get perfect results. You will get uncertainties, okay? And these uncertainties will depend on the size of the experiment and so on and so forth. Okay, so in practice, you don't even know these, okay? So our third example is basically coin, okay, coin, and you are so bored in your life that you will basically keep tossing the coin an infinite number of times. You will never stop. You'll just take it, toss it. Keep doing this forever, okay? So now we start talking about something called infinite experiments, an infinite sequence of experiments. Of course, in practice, we can never do an infinite sequence of experiments, but this is like a mathematical idealization that can be useful when we analyze situations in which we do an extremely large number of experiments. So consider an infinite sequence of independent coin tosses, and the probability of getting ahead in the nth toss is Pn. So it is not, basically the probability of getting ahead is not like 1/2. It may actually depend on the toss. So, it may be when you toss for the first time, the probability of getting ahead is 1/2, then it's 1/3, then it is 1/4, then it is 1/5, and so on. And maybe the probability it changes in some other way. Okay, but the probability depends on n. Now we ask about what is the probability of getting heads infinitely often. Infinitely often, which is abbreviated as IO. So if you have not seen this before, so let's first, maybe this will be the last part of the lecture. Let's talk about what actually does it mean to say the probability of something infinitely often, because this is not just a word, it's a technical expression with a certain meaning. Okay, so let's focus now on this infinitely often business if you don't know it from some previous course. So let AN be the event of getting H in the nth toss, and again the probability of AN depends on n. Okay, so it's not a fixed number. Of course, being fixed, if it does not depend on this, will be a special case in which the probability for each toss is exactly the same, but we are allowing for the probability to be different from toss to toss. Now, here it may be good actually to think about the sample space. What is the sample space? Definitely it's not head-tail. Definitely it's not head-tail, because we are not just tossing the coin once. It is not, it is not a sample space composed of two elements, head or tail. Actually, our sample space, in each experiment you will do, again, you will just take a coin and keep flipping it ad infinitum. So it means that each element in the sample space is an infinite sequence of heads and tails. H, H, T, T, H, T, and so on. Okay? And so if you replace the H by 1 and the T by 0, for example, then actually our sample space is equivalent to the set of all possible infinite sequences. No, so it is exactly, so it is an uncountably infinite sample space. Why? Again, because it is basically the space of infinite sequences of head and tail. You can think of it as the infinite sequences of zeros and ones. And in the first lecture of this course, we basically did the proof with the diagonal argument, exactly the diagonal test, that basically this set is strictly larger than the natural numbers. If you assume that basically each of those sequences can be basically indexed by natural number, you can obtain a sequence that is outside our list. So in the first lecture, we proved that basically this is uncountable. It is something with a cardinality that is strictly greater than Aleph node. So big omega is basically each element in big omega is an infinite sequence of H and T. Okay, and so big omega is uncountably infinite, and you can actually say that the cardinality of big omega is a small c. Now to the definition. What is the probability of an infinitely often? An means obtaining a head in the nth toss, and typically what this is what you will see. ANIO, infinitely often. Now it is expressed as such. So infinitely often is this thing here. You know, it may look scary to you, but this is the event we are talking about. When I say an infinitely often, I am talking about intersection m being a natural number, union n greater than or equal to man. What does this mean? Okay, so this is the explanation. This event here, basically, we are talking about all elements in big omega, and each element in big omega is an infinite sequence of H and T. So we are talking about the probability of a subset of big omega. What is this subset? What is this subset of big omega we mean or we refer to when I say having a head infinitely often? So we are talking a subset of big omega such that, so this is how we define our event here. For every m that is a natural number, for every m that is a natural number, there exists an n that is, of course, is a natural number, but it's a natural number greater than or equal to m, such that omega n is equal to h. So what does this mean? So we have a sequence. Each element in omega is an infinite sequence. Head, tail. So this is the first position, second position, third position, and so on. So we will include an infinite sequence in our an infinitely often event. If for every m, so you choose a natural number m, let's say that this is m, it's here. So you pick the nth position in the sequence. What should happen is that starting from m and higher, you must have at least a head. Union n greater than or equal to m. So we should have at least an h here. If your sequence has this property, then it is part of the subset of big omega that we are interested in, the so-called getting heads infinitely often. Okay, so the last thing. So if you have the all T sequence, is it with us? Of course, no. You know, basically, if you pick m equals 1, for n equals 1, there is no head that is after, you know, the m. There is no head whatsoever. So this is not part of the sequences we are interested in. Suppose that you have a sequence TTH, TTTT, and so on. So after this H, we don't get any head afterwards. Is this sequence part of what we are interested in? No, because if you choose M to be here, then starting from here to infinity, you never get a head. So this is also excluded.